In Chapter 6, we begin speaking about one of the most important examples of a continuous probability distribution. And if you watch Dr. Mosley's videos, he does go through a little bit of this explanation. So just to kind of reiterate a little bit, the normal distribution, again, is very, very important for us when we get into inferential statistics in the next couple chapters. So we need to look at the graph of a normal distribution, which is called the normal curve. Sometimes you may have heard of it as the bell-shaped curve. Part of that is it is bell-shaped and symmetrical. It's a symmetrical curve that's bell-shaped. Some people call it mound-shaped. Approaches the horizontal axis but never touches it, and the inflection points occur at the mean plus or minus each standard deviation. So when you think about that, think about a histogram. If you did a histogram and put a smooth curve over it, the shape of it would be bell curve. Remember we talked about left skewed, right skewed, symmetrical. There's two parameters, the mean, which is mu, and the standard deviation, which is sigma. The total area under any curve is actually equal to 1. So Dr. Mosley talks quite a bit about in his second video about the empirical rule. So if we have an idea about an empirical rule, let's say we have a distribution of housing prices in Ohio. Let's say the mean is $150,000 and the standard deviation is $20,000. So I'm going to draw a curve that looks like a normal curve here. The mean is the measure of center. In a normal curve that's symmetrical, the mean is always at the center. Okay, so our mean here is 150,000, right? Okay, if we look at what housing value is one standard deviation above the mean, that means we would add one standard deviation. So we say 150,000 plus 20,000. So we'd have 170,000. That's one standard deviation above the mean. We can go the other way and say one standard deviation below the mean is 130,000. Right? So I took the mean, added one standard deviation, took the mean, subtracted one standard deviation. In symbols, that's often written as 1 plus or minus 1 standard deviation. Sometimes they won't even say the 1. Okay, that's what we just did. One standard deviation above, one standard deviation below. Now we can do the same thing for 2 standard deviations above. Add another 20, we have 190,000. And 2 standard deviations below would be 110,000. Okay, so this is 1 standard deviation below and above the mean. This is 2 standard deviations above, 2 standard deviations below the mean. And then we can do the same thing for 3. We have 210,000. If we add another 20,000 and subtract 20,000 here, we'd have 90,000. So these are 3 standard deviations above the mean, 3 standard deviations below the mean. Okay, so if we talk in terms of number of standard deviations, this is 0, right? It's right at the mean. So we said this is 1 standard deviation above the mean. This was 1 standard deviation below. When we say below to the left, that would be like a -1. This is 2 standard deviations above the mean. This is 2 below. That would be like -2. This is 3 above. This is 3 below. Okay? We call these z-scores. They tell us how many standard deviations above or below the mean they are. And I'm going to consider this just my x scale. That just means whatever my variable of interest is. Okay? So in section 6.2, it will get into how we convert these into z-scores, and it gives you the standardized formula. So these z-scores go with what's called the standardized normal curve. And you'll hear that a lot because it helps you to compare things. So if we say there's a house that's $300,000, okay, that is a large house, expensive house. Based on our distribution here in Ohio, that's larger because 210 is right here, so 300,000 is over here. So it's more than 3 standard deviations above the mean, correct? But looking at the standardized score will tell us where that is. If we're looking at somewhere in California where the mean is 300,000 with a standard deviation of 20, that's not very expensive because it's not going to be very far above the mean. Make sense? Okay, Also in 6.1 though, it does talk about the empirical rule, so I want to talk briefly about that here. And this is just an introduction to really 6.2. We'll talk a little bit more about in 6.2 the z-scores. But I wanted you to see how they look on the curve. What the empirical rule tells us is that within 1 standard deviation of the mean, 68% of our data lie. That means, according to this distribution, 68% of houses are between 130,000 and 170,000. Okay, and that's where we write within 1 standard deviation of the mean, plus or minus 1 standard deviation, approximately 68% of our data lie. Okay, what the empirical rule tells us is within 2 standard deviations, 95% of our data lie. So that means between 110 and 190 is 95% of your data. Okay, within 3 standard deviations, 99.7% of your data. So that means from here to here, 99.7%. Okay, now because it's symmetrical, we can break these little sections into percentages. Okay, symmetrical, if this is 68%, I know that this is 34% and this is 34%, right? Same thing is true if you know this distance here is 95%, I can find these two chunks by saying 95 minus 68 divided by 2. And I think Dr. Mosley shows this a little better in the video. Or 13.5% of your data is here and 13.5 here. Make sense?